Hello everyone, and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, we extended the transform and script components of our entities with the functionality that enables us to update entity position, rotation, and scale. However, we didn't get around to actually using this new functionality, and we also still need to fix our render. So today we are going to rotate this 3D model around and fix the rendering issues, as well as do a couple of other improvements to the code. I'll clean up this entity creation function a bit first in order to make it easier for us to create game entities with a rotator script attached. It now takes the entity rotation and position and whether it should be rotating. So now we get the rotation and position directly from the function parameters. If the entity should rotate, we include the script creator function pointer, which will instantiate our script when the entity is created. When we create a camera, we set the position and rotation as before. The game character is centered in the world and rotates about its y-axis. I'll also write a function that removes the game entity. We are not going to use it right now, but we'll probably need it later. Before we test our code, I'd like to initialize the frame info more explicitly to avoid making errors and omit or interchange values by accident. Because normally the script class is declared in a header file and this macro is used in the CPP file, it would already know about the script class. In this case, however, we didn't declare the script class in a header and therefore we need to forward declare it. We can run the test application, but our character is not moving because we still need to call script update function. We need to call it here for each frame and pass the frame time. Right now, our timer class doesn't have a function that returns the average frame time. Fortunately, it's easy to add since we already calculate it here. I'm not returning MS average directly because it gets reset to 0 every second. Instead, we use a copy. Well, it works, but it's spinning way too fast. And that's because we are passing the frame time in units of milliseconds instead of seconds. To convert this value, we should divide it by 1000. That looks a lot better now. Let me quickly increase the precision of our timer here, because as you can see, when the frame rate increases, measuring frame time in milliseconds is not accurate because of rounding errors, and as a result, our model's rotation seems to be slower. To fix this, we can use microseconds instead. Note that now we have to divide the frame time by 1,000,000 in order to convert it to seconds. I'll also change the variable name to reflect the time units that we are using. Now the model is rotating at the same speed as before. Okay, time to fix the graphics. First, observe that the model seems to be inside out. It looks like we are rendering the triangles that are facing away from the camera. In other words, we are rendering back-facing triangles instead of front-facing triangles, which would explain why the model appears to be inside out. In Primal Engine, we are using a right-handed coordinate system, which means that the order of vertices that define a triangle should be counterclockwise. This is also known as counterclockwise winding order of the triangles. However, the default winding order in Direct3D is clockwise, and I would guess that that's because of the left-handed origins of this API. In order to change this default, we can set this rasterizer state to 1, which will tell the API that we are using counterclockwise winding for front-facing triangles. Unrelated to winding order, I'll also disable multisampling since we are not using multisampled render targets. Now the model is rendered correctly. Notice how the shoulder extension bits are indeed on the right shoulder. Also note that the normal vectors which we are using to color the image are changed to bluish instead of red and green. If it's not already clear to you why this happened, then please feel free to take a moment to think about why this makes sense. The next issue that we need to fix is the aspect ratio of the camera. For some reason, it seems that when we resize a window, the aspect ratio is not updated, and that causes the rendered image to stretch and deform. Looking at the camera setter functions, we see that I'm passing the camera instance by value, and therefore the updates are being applied to a copy of the camera instance. Obviously, this is wrong, and we can fix it by passing the camera by reference. Resizing the windows now will correctly update the aspect ratio of the rendered image. Let me also quickly check if the transform cache lookup using linear search works as intended, which appears to be the case. Before we move on to the next topic, I'd like to spend just a couple of minutes to do a few code improvements. First, I'd like to move these two lines to prepare render frame function, because filling per object data is also part of preparing the frame. Instead of passing the constant buffer reference as a function parameter, we can directly access it in the function. The next improvement is a bit more complicated. It's about creating pipeline state objects, and as we know, a substantial amount of work is done on the Direct3D and graphics driver side when a PSO is created. All kinds of validations take place, and possibly shaders need to be compiled from the bytecode that we provide into a format that's specific to the graphics card that's present on each machine. In our current implementation, we lock our data during PSO creation. During this time, the data can't be accessed for rendering, and therefore we are practically blocking the renderer. If you'd leave it like this, we would eventually see some frame stutter when a lot of render items are being created. To prevent that from happening, I'll separate the pipeline state data from render item data and add a mutex specifically for pipeline state objects. Using this mutex, we only lock PSO data when we need to access them, which happens rather quickly. We are just looking up a key value pair and add or remove an item from an array. We need to isolate the PSO data access from PSO creation itself in this block of code. So when creating a PSO, we'll put it in a local variable instead of adding it to the array of pipeline states right away. After PSO creation, we can lock our data and add it. This way, creating PSO can happen in parallel with rendering, which in theory wouldn't cause any frame rate problems. Here we also need to scope the material lock so that nothing is locked when we try to create a PSO. Note that reading material data doesn't take that long, and also that getting compiled shader pointers by calling getShader function is already thread safe. I thought that this would be the last improvement for today, but now this line of code caught my eyes and reminded me of the fact that we would like to improve depth precision by using reverse depth buffers. Let me explain the problem with depth precision first. Starting with a refresher of the projection matrix, which I discussed more in detail in this video. Given any point in view space, which is a space relative to the camera's coordinate system, with the camera at the origin, the projection matrix will map that point to homogeneous clip space. We see that the W component contains the negative Z coordinate of the point. This is because we want to fit every point in homogeneous clip space into normalized device coordinates, and to encode depth information in a range between 0 and 1, we need to divide this vector by the value in the W component. This is called the perspective divide, which brings our point fully into the NDC space. Again, I already made a video about this, so if you'd like a more detailed explanation, please go ahead and watch that video. Now, if we look at the Z coordinate after perspective divide, we see that it's no longer a linear function because of the division by Z. If we plot 1 over Z, we can clearly see that it's not a straight line. Instead, it uses up a lot of precision of the normalized depth value in a relatively small region close to the camera, and quickly loses resolution at points that are farther away. This will introduce artifacts when rendering far away objects that are close to each other, which is also known as Z-fighting. Fortunately, there is one easy to implement trick that considerably improves depth precision, which is done by simply reversing the depth range in NDC space. So on default, the depth value ranges from 0 for near objects to 1 for far objects. If we instead use 1 for near objects and 0 for far objects, the nonlinear distribution of points in 1 over Z will be cancelled by increasing precision of depth values when approaching 0. In this graph, we can see that the resolution worsens rather quickly for default floating point depth. However, it remains well behaved when using the reversed depth. I'd like to recommend reading the articles linked in the video description for better understanding of depth precision in general. I also need to mention that this only works if the depth range is within 0 and 1. In Direct 3D, reversing the depth buffer is actually rather easy. In fact, we already wrote part of the code that involves the depth stencil state description. As you can see, we already have reversed and reversed read-only states. Looking at the enabled read-only state, we can see that the comparison function is set to less than or equal. That means that any pixel depth value that's less than or equal to the value in the depth buffer will overwrite it. Which makes sense because pixels that are closer to the camera have a smaller depth and should be in front of the objects that are farther away. In reverse depth, however, the objects closer to the camera have a larger depth value in normalized device coordinates. Therefore, comparison function should be set to greater than or equal in order to overwrite smaller depth values. So during PSO creation, all we have to do is to use the reverse depth stencil states instead. Oh, I see we didn't actually finish the PSO threading code yet. I forgot that we need to lock our PSO data as well as the render item data when we are getting render items. Don't worry about this squiggly line, it's just Visual Studio being clueless again. Okay, going back to reverse depth code, now we need to clear the depth buffer to 0 instead of 1, because 0 represents the farthest distance in the depth buffer, and 1 represents the closest distance to the camera. Running the program like this, we can see that the image appears to be inside out again. We can fix this issue quite easily by simply swapping the near and far planes of the projection matrix. We can do this by swapping the near z and far z parameters when constructing the projection matrices in camera's update function. Now the image is rendered correctly. Let me also set a bit more sensible depth ranges for the camera initialization, although as we saw earlier, reverse depth holds up pretty well for these values. The next topic that I'd like to show you in preparation for the next video is compiling shader variations. To illustrate this, let me load a model file that uses different vertex formats. Till now we have been only using one vertex shader that can work with vertices with normals and UV coordinates. Let me show you what happens if I replace our current model with one that uses different vertex formats. So I'm going to back up the robot model and export this other model by opening it in the editor. Now we have a new model file here, which will be loaded as soon as we start the test application. In this function where we cache the mesh information, we can see the elements type enumeration coming in, which is 1, and if we let it loop a couple of times, we eventually get a submesh that has elements type 3. I'm not going to let it run because it could crash the driver and the OBS recording software, which I don't want to happen while recording this video. Looking at the elements type enumeration, we see that type 1 only has normals and no texture information, while type 3 has both normals and UV coordinates. So we need to find a way to compile shader variations based on what type of vertex elements are used. Compiling shader variations is the topic of the next video. However, we can already write our vertex shader in a way that can be compiled into different variations. This is done by defining a compile time constant for each of elements types and write shader code for each one of them. That's what we are going to do eventually, but at this time we don't have skeletal meshes that could be animated in the vertex shader, and writing 2 shader variations for our current model will be enough. Here I am basically just creating the same enumeration and make it fit with our HLSL formatting, which is camel case for some reason. Now, instead of defining different structures for each vertex element as we did in C++ code, I'm going to create one structure that compiles to different variations for each element type. We can use the compile time definition to tell the compiler which variation it should compile. For each of these types, we can define the elements format, which should be the same as the C++ format here. For the two elements types that we would like to define, we can simply copy from the old structure. Then we can remove it, since we are going to be using this one for all types. Next, we need to write a vertex shader variation for each type. Before doing so, I'm going to make the code that we have here a bit more compact. And then I can duplicate this code because we don't have textures yet. Later, when we use textures, the code will obviously be different for each variation. Running test renderer, we can see that our model is rendered black because we haven't compiled any vertex shader that reads from the element buffer. And that's what we are going to continue with in the next video. As always, I appreciate all your support, whether it's through Patreon or by subscribing to this channel, or if it's simply by watching this video, you have my sincerest gratitude. Thank you for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!